oscillations of loaded spring. The question will be, show oscillations of loaded spring SHM, find time period. Question is, show oscillations of loaded spring R SHM, hence find time period. So this is a spring A. This spring is loaded. This is the length extended when it is loaded. M mass is attached. This is figure B. The spring is stretched. To distance y, this figure is C, and left the spring will start oscillating. Again, spring, it is loaded. This will be the equilibrium position now. Some length will increase. This L is increase in length. Now it is stretched a length y and left. The spring will start oscillating. Take a spring, suspend it as shown. Load it by mass M. L increase in length. In figure B, in equilibrium position, F1 minus mg and F1 minus KL minus KY. F1 restoring force. L increase in length, so it is Ky. As they are in equilibrium, the forces are equal and opposite. From first and second, minus Ky minus mg minus with minus, the value of force constant of this spring is The elongation was L. Number third. Up to here this spring is not oscillating. Now stretch this spring, loaded spring, to distance y and leave it. It will start oscillating. Then retarding force, that is F2. K is spring constant Y plus L. Now total elongation is this. Net force for oscillations, that is F. It will be F2 minus F1. F2 minus K Y plus L minus F1 minus KL. F1 F2 minus F1 minus KL minus KY minus KL plus KL, or F minus KY. Fifth, therefore, F directly proportional to Y. Hence, fourth property, restoring force minus restoring force directly proportional to displacement. Hence, motion of loaded spring is SHM. Now time period. That is D 2 pi m by K, where K is spring constant. Force constant, here it will be spring constant. 2 pi m K. mg by L from third. Or T 2 pi. M goes with M. L by Z. That is time period. is independent on mass loaded to spring. So the question is, show motion of loaded spring is SHM, hence find time period. Oscillations of loaded spring in combination this is spring, this is another spring, different materials, this is the mass, they are loaded. K1 spring constant, K2 spring constant, this is point of suspension. So this is first case. Spring combination is as shown. K1 spring constant of first spring, K2 spring constant of second spring, M mass loaded. Let Y extension in length of springs. As these are different, so restoring force will be different. Because length is same, this is different, length same, then F1, F2 will be different. If K1, K2 are same, then forces will be same, but these are different. Different materials are there, springs of difference, different spring constant or force constant. Net restoring force, that is F. F1 plus F2. Therefore F1 minus common, L common, third, but F KL, K spring constant of combination fourth, compare third and fourth, minus KL L goes with L, minus with minus, K comes out to be fifth, hence time period that is D 2 pi m by K or T 2 pi m. K is K1 plus K2. So the question is, derive expression for time period of loading springs in combination. This is that expression of time period as shown. The combination is as shown in figure. Now second case, spring, this is that mass, spring, a fixed, it is given, it is K2. Combination of springs as shown. L displacement of mass either upward or downward. ये downward displace कर दिया L, Y as you wish, चलिए Y is displacement. K1, K2 spring constants. Then F1 K1y, F2 K2y. As these are different, displacement is same. This spring decreases by y, this spring increases by y. Displacement change in length in both cases same. If they are same, they are different, so forces will be different. Hence, net restoring force, that is F. It is F1 plus F2. minus y k1 plus k2 third, but f is minus ky fourth, k spring constant of combination. Comparing third and fourth, minus ky minus y k1 plus k2 minus with minus y with y, so k comes out to be k1 plus k2 fifth. So this is net force constant of combination. Hence time period that is t 2 pi m by k, t 2 pi m by k. So result of both combination is same. Now third case, this is first spring, this is second spring, and this is the mass. This is K1, this is K2. Spring combination. As shown, K1, K2 are spring constants of springs. K spring constant of combination y net increase in length when mass m is loaded. Y1 increase in length of spring whose spring constant is K1. Y2 increase in length of spring K2, then y will be y1 plus y2 number first. Now y. Now f minus kl. And f minus k1l. Also f minus k2. It is y, it is y1, it is y2. Same force is on combination, same force on this, same force on this. So y comes out to be minus f by k. y1 comes out to be minus f by k1. y2 comes out to be minus f by k2. Putting these values in first, y minus f by k minus f by k1 minus f by k2, or 1 by k comes out to be 1 by k1 k2, k1 k2 LCM, or k comes out to be second, but time period that is t, 2 pi m by k, time period 2 pi m by k k1 k2 by k1 plus k2, or time period 2 pi m k1 plus k2 k1 k2 third. So this is time period of springs in combination. Undamped oscillations, undamped oscillations, cycle oscillations A, one amplitude. This is amplitude, one amplitude of oscillations is constant, then oscillations are undamped. Oscillations. Example: AC, alternating current. They are undamped oscillation. Damped oscillations. This was the amplitude, then goes on decreasing. These are damped oscillations. When amplitude of oscillations goes on decreasing, when amplitude of oscillations goes on decreasing, then oscillations called damped oscillations. Amplitude, this is amplitude, maximum displacement, ये कम होगी और कम होगी. Damped oscillations. Example: oscillations of tuning fork, सोनोमीटर वायर. ये क्या है? डैम्प्ड ऑसिलेशन. फोर्स्ड ऑसिलेशंस. When a body oscillates with a frequency other than its natural frequency, then oscillations of body are forced oscillations. Suppose the natural frequency of this board is 20 oscillations per second and it is made to vibrate 30, 40, 50, then those oscillations of this board will be forced. Again, natural frequency 20 hai and it is made to vibrate other than 20, then the oscillations are forced oscillations. Resonant oscillations. Resonant. These are also forced oscillation. Board frequency 20. Marker say 30 and marker made this board to vibrate with a frequency of 30. So these are what? Forced. 40, 50, forced. Now again listen what I say. Vibrations, oscillation 20, marker 30. If marker made this board to vibrate with a frequency 30, not other than 30, then these are resonant oscillations. What I said, frequency is 20 hertz of this board, and of this marker it is 30 hertz, and marker is placed here and board vibrates with 30. 20 थी इसकी 30, ये भी 30 से वाइब्रेट करें. The vibrations are forced vibrations, and in this case they are resonant. इसी की फ्रीक्वेंसी मार्कर की फ्रीक्वेंसी बोर्ड वाइब्रेट करे. Resonant vibration. When a body vibrates with a frequency when a body vibrates with a frequency of other vibrating body. When a body vibrates with a frequency of other vibrating body, then vibrations of first body are resonant vibrations. So resonant vibrations are also forced, but special type of vibrations. जो बॉडी वाइब्रेट करवा रही है दूसरी बॉडी को अपनी फ्रीक्वेंसी से करवा रही है, दिस इज द मीनिंग ऑफ रेजोनेंट वाइब्रेशन. ए क्वेश्चन, glass windows of houses near a railway line are generally broken. Why? Frequency of glass is small. When train passes then glass windows vibrate with the frequency produced by train. resonant vibrations. जो ट्रेन पैदा कर रही है फ्रीक्वेंसी, उसी से ग्लास वाइब्रेट, सो ब्रोकन.